welcome to the SoftBoarders. Today we're going to be working with the problem of invert binary tree. So the invert binary tree is given a binary tree. A binary tree is of the form of a tree node, which has the and you're given the root in the question. And the binary tree is just a tree node which has a root, which is a value, could be an integer, could be a string. So in our example, it's an integer. It also has a left child, so which is also going to be a tree node. For the left child for 1 is 2. And similarly, it has the right child, which is also a tree node. In this example, it's 3. So the invert binary tree, all it wants you to do is if you're given a tree node, let's say 1, and it has children 2 and 3, you return the tree node and you invert the children. So you get 3 and you get 2. So it seems pretty straightforward, but we're going to break it down by the base case. So let's say we're given this example with a tree node 1, which has a left child, but it doesn't have a right child. What we need to know right away that it actually does have a right child. It's just null, and it's just not represented. So when you're trying to invert this, you actually do 1, null, and 2. As you can see, when you encounter a null, we can just return a null right away. If this 2 had another layer to it, so there was a 3 and a 4 over here, this example would have also inverted the children of the 2 right here. So this would have returned a 4 and a 5. So we can clearly see this as a recursive call, where in every single, whenever you encounter any node, you swap its children left and right. But and then you just at the end of it, you just return the node. If your current node that you're on is a null, you can just return null because there's nothing to invert. So as we clearly saw, our base case would be something like if root is equal to null, then we return null. Okay. And so in the last example, if you had child nodes, you invert the children as well, and then you return the node. So we would create a temporary left, which would hold the inverted right child because you're going to swap it. So we can do the variable left is equal to, which is it's going to be the inverted right node. So the two's place is going to be the 3. So let's give it a function definition. So it'd be something like function of, let's call it invert. So a function invert, and it's given a root, which is of, let's say, type tree node. Okay, so when you create a variable left, so left is going to hold invert of root right. And then we have, similarly, do the same thing for the right child. We create a variable when we're done creating the left and the right variable, we have to assign the root's children. So right now the root is still not modified. So to do that, you just do root dot left is equal to the left variable we just declared, because the left is the inverted right, so it would be left. And root dot right, similarly root dot right is equal to the right, because the right is the inverted left node. So now we know we swap the last two, and once we're done that, we can just return the root. So we'll just return the root. And then answer here. So this should be pretty straightforward. So let's actually walk through the runtime analysis. So for a given question, we are, as you can clearly see, we're calling the invert function on the left and the right of the node. So what's eventually going to end up happening is we're at 1, we call the invert left, invert right. So you look at this guy, and then we look at here, and then we go back up, and then look at, come down here, and we resolve it back up. So as you can clearly see, we're visiting every single node. So the runtime is O of n. N is the number of nodes that you have. So the space complexity, on the other hand, is actually not O of n. You're starting off at 1. And our first recursive call is we invert on root.right. So we're going down here. Then, when we're down here, we go down one more level to root.right. So you go down here. And then once you're here, you try to do root.right again, which is the null, and it'll come here. And then we go all the way down for the height of the tree. And then once we resolve this, we come back up here, when you're here, you check its other node, other null on the left child, because that's what the right function's doing. But as you can clearly see, and then after this is resolved, we come back up here, and then we go down here. So this clearly shows us that we're only going down the height of the tree at any given time. And then we make it back up and then down. This means the space complexity is actually O of the height of the tree. And if you've done a data structures class, you know the height of the tree is actually just O log of n. And that is the solution to invert a binary tree. Thank you.